Okay, so I have a little bit of more time. Okay, cool. Then I will just briefly also show some ideas in the space of continual learning. So one other thing that we usually see is or what we want to achieve is we also want to learn, for example, single tasks continually. And because one of the major disadvantages, or what we see a lot, especially also if you're using machine learning methods to detect anomalies in ERP data, and also, for example, using autoencoded neural networks in detecting fraud in ERP data, we have still this high number of false positives to a certain extent, depending a little bit on the data set, especially in audit engagements where you try to audit large volumes of journal entry data. And one idea that is, evident in the deep learning community for quite some time already is the idea of continual learning, or for example, lifelong learning. And there was a very famous DARPA workshop in 2017 about it, where the idea was really to develop next generation ML technologies, and especially systems that could improve from experience and to continuously learn and monitor certain ML systems. So that was the idea that part of the time, because what was one of the main motivations for that a couple of years before, and this was just one solution that DeepMind developed in 2017 to the challenge, is this challenge of catastrophic forgetting in deep neural networks, meaning that neural networks actually learn or unlearn certain experiences over time. So what does it mean from an audit perspective? If you go back to our initial audit autoencoder example, and we think about, for example, maybe our population of journal entry, and the journal entries of a particular data set of a particular fiscal year, for example, are generated by different departments. So let's assume, for example, we have 3 sales departments, 2 asset management departments or asset depreciation departments. We have a fraudulent department, and then we have an HR process where we have a new HR process that replaces an old one. And if we just look at the volume of the journal entries that are generated by all these different departments, just a singular input, for example, then we see, for example, the sales department here generates a lot of journal entries, this only a few, and this a little bit more, and our fraudulent department generates a little bit more journal entries than our sales department. If you feed this kind of data distribution through our autoencoder neural network, what's happening basically is that most probably it will learn very nicely to reconstruct the journal entries of the first sales department, maybe not so good the ones of the second sales department, because we have a very limited number of journal entries, and so on. But at the same time, maybe our fraudulent department that we see here is not detected as fraud, because we still have a certain amount of journal entries that are generated by this fraud department. There's a very a huge simplification that I'm doing here, but still, there's this high chance of so-called false negatives that we are generating. But if we would have also considered, for example, the posting activity over time, then maybe what we see is, for example, for this sales department that we see here, there was a decline in the sales over time. So it seems like this is just a natural progression of what we saw before. And therefore, we are generating here a high number of false positives. Right? Same holds for the asset department. It has in general a very, very low posting activity. So this posting activity, this very limited number that we see here, is also not surprising. So again, maybe our autoencoder generates a high number of false positives here. And at the same time, as I mentioned, the fraudulent department, since there's a lot of fraud activity going on at that particular period, maybe that corresponds to a false negative. Could be. This is just hypothetical. So the question was also, can we make this work, or can we make continual learning work for the purpose of real-world financial statement audits in order to reduce even further the number of false positives that we're generating using the autoencoder? And this is the whole idea of continual learning, basically saying, okay, we go, for example, to a particular audit client at a particular audit season, extract the data out of the ERP system, and then, for example, feed it through the autoencoder neural network based on a reconstruction error, derive anomalies, and then investigate those, and then come at the next audit season again, extract the anomalies, train the autoencoder neural network, and so on. So what we want to achieve ultimately is we want to cope with these different data distributions, or this shift in the underlying data distributions that we see from one audit season to the other audit season. So this is what we're seeing. And one idea in order to accomplish this is the idea of so-called sequential fine-tuning of deep neural network architectures. It's a very simple technique, just saying, for example, we want to, once we have trained this model here at a particular audit period, we take all the parameters and then fine-tune it based on the new data that we are receiving at the next audit period. So we're just taking the model that we got from one audit period, and then continue the training based on the data that we get for the next audit period, in order to not forget what we have learned in the first audit period. This is as I mentioned, the idea of sequential fine-tuning. Well, the challenge with sequential fine-tuning is that it is prone to catastrophic forgetting. So we will abruptly lose some information of previously learned tasks if we follow these simple techniques. So let's assume, for example, we have our autoencoder neural network and we have our data distribution for the first audit period, and we initialize our autoencoder neural network with a certain set of parameters. With progress in training, what's happening is then we are moving these parameters, and this is a very high dimensional space of all the parameters, into a certain regime in this high dimensional space. So we are moving from the initialization to an optimum number of, or to an optimum set of parameters for this particular data set that we see here. And then once we apply this for the next audit period, we will and then fine-tune the autoencoder neural network architecture and the parameters based on the next data set. We'll probably move to another optimal regime here for this data set if we train it long enough. But at the same time, we're probably leaving the optimum regime for the first audit experience, or for the first data set that we have. And then if we continue this for the third data set, we are maybe converging to a new regime where we somehow perform well on the first data set, but maybe not good anymore on the second one and perfect at the third data set. And this is the challenge of catastrophic forgetting. So we somehow forget maybe to a certain extent to perform well on the second experience data sets. And what we ultimately want to achieve with continual learning is basically, we want to always stay in this regime, for example, where we could perform very good at all the different data sets that we see, or data modality sets. So this was one of the workshop papers that we just published beginning of the year, where we tried it on a very simple toy scenario. And these are just some results that I picked. For example, let's assume we have a sales department here. So we see this declining activity over time. So what will happening then is with progressing training is that, and this is the current audit period learning, is that since we only see a very limited number of posting at our audit period at the end, these postings will correspond to a very, very high reconstruction error based on the autoencoder learning setup. And at the same time, we have a fraud department. It's exactly the case that I mentioned before, where we see a limited number of postings, but still more than, for example, as we see for the sales department. And this is the department 42 here, for example, where we have a lower reconstruction error by just applying, for example, this standard learning technique without sequential fine-tuning or with any continual learning setup. And therefore, we have a lower reconstruction error. And most probably, we won't start investigate in a worst-case scenario. This department, this fraudulent department, we would maybe focus to a certain extent on the sales department and see what's happening, depending on the time budget constraints that we have. The interesting thing is, just to speed it up, I mean, there are a couple of continual learning methods. And one is, for example, the idea of replaying certain samples from the past. An interesting thing was what we see here quite nicely. If we use experience replay, which is one of the continual learning techniques, we see quite nicely that the department that corresponded to the declining sales here, it receives a very low reconstruction error. And the department that corresponds to the fraudulent activities, since we don't have any experiences before, has a higher reconstruction error. And this is exactly what we want to achieve. So this is just one example where the continual learning could help us. Does this make sense so far?
And actually, when I see this result, will this affect the better performance of a continual modeling learning affected by the expanded data points rather than, because if we use standard current audit period learning, we focus on the specific periods data points. Right. And when you use the continual modular learning, you like use the cumulative data points overall.
Yeah, exactly. So one approach would be, and this is a very good question. I mean, in order to solve this problem as well, is what you can do is maybe going back and say, instead of just extracting all the journal entries of a particular audit experience or of a particular audit period, I would go back maybe, for example, and extract from our client maybe all the data from the last 10 or 5 audit seasons, right? But this is usually very cumbersome if you want to extract so much data from the client. Usually the clients are also not happy about it to a certain extent. And therefore the question arose, okay, can we accomplish the same effect to a certain extent by just using a continual or more clever learning technology, rather than always extracting large volumes of data, of historic data as well from the client in order to minimize our false positives.
Okay,
that's the idea. So the upper bound is definitely extracting more data from the client. That's, I mean, to a certain extent, always possible, but of course the clients maybe don't like this ultimately.